Okay. All right. Thank you guys so much for coming, especially between AGU and leading up to the holidays. I want to welcome Ryan O'Loughlin and Dan Lee. Ryan is an assistant professor in philosophy at Queens College, and Dan is an assistant professor, also philosopher of science at Baruch College. So I don't know if some of you are aware, Ryan was previously here in the spring where he gave a talk about how bad models are helpful in climate science. And after that, there was a lot of sentiment, both from Dan and Ryan's side, as well as our side here at GISS, that it would be really cool to have more discussions about philosophy of science and kind of make this a regular thing. So this is the first of hopefully more science philosophy talks. I think we're having you guys come back in February. Mm-hmm. Yeah. Yeah. So I will just turn it over to you guys. Grab me some water.
Dan, do you want to?
I'll start. Thank you so much for having us today. As you can see, Richard Feynman says philosophy of science is about as useful to scientists as ornithology is to birds. This is a quote that I actually completely agree. So we're here not to lecture birds on how to fly, instead of learning from the birds about how to fly. But hopefully this could be a mutually beneficial learning experience, because just imagine if birds could read, then the ornithology studies would have been helpful for them to understand what they're doing. The first thing that we would like to do is that we're college professors, so we like in-class activities. Thank you for entertaining us. We'll pass on some worksheets. This is an exercise that will transport you into 17th century. And now I know you're scientists from the 21st century. Let's see how well you do if you were a scientist back then in the 17th century.
Also, if you're on your computers, we sent this out in the reminder email, so you should have a copy of the worksheet there as well.
Sure. I remember that worksheet. Okay. You can start reading a small historical episode that's repeatedly taught in history textbook. I mean, the middle school students know about it. But let's see how well you do as a 17th century scientist.
Perfect. Thank you. There you go.
Don't turn onto the second page yet. Just focus on the
At the bottom of the first page.
Oh, okay.
I didn't read the pause here.
This is the historical case that many people know. How did we shift from geocentric model to the heliocentric model? And Galileo was able to find a crucial piece of evidence about the base of Venus. Have you made your decision about whether to support or refute Galileo's discovery?
Do people need more on the first front page, or we want to put it to a both?
So we're thinking as a current scientist, or we're thinking how things were back then in 1610?
Yeah, imagine you have access to the same information that a scientist would have had access to.
Yeah, you're a 17th century scientist.
And same society and same, you know.
Politics.
And if you get it
Same
wrong,
powerful
you're
church.
gonna have burnt to the stake. So the stakes.
Yeah, and pretend that you're
Same
not
consequences
influenced by the
remain.
Catholic Church.
Right. We're saying what about the Catholic Church?
Pretend you're not influenced by the Catholic
Okay.
Church. You have your scientific spirit. You want to know what's the truth
Oh,
about the solar system.
that matters probably then.
You don't,
That does change things.
Well,
Whatever one place you could actually have free thought.
Do you all make your choices to support or to refute, Gallio's argument?
I'm sensing this is a trick question. You asked me.
I had my question.
Okay. Use your best judgment as a scientist.
Yeah,
What's-
maybe Show
Okay.
of, show of hands, who'd support Galileo's?
Yeah.
Well, congratulations, you're all on the right side of history. Right, but history is never pure nor simple. It's much more complicated than that. So please turn to the second page, and there's some new information that just comes in about Galileo's observation. In the same year, Galileo also observed Saturn. And you see his sketch in figure 4 and read his description.
The simplest progression around not the cycle for some you would get for places. Go back to one.
Still use your best judgment as a scientist. Would you say that Saturn is really like this, having ears? Or you just can't help but wonder what's going on with, maybe it's something that's wrong with Galileo's telescope? What would be the hypothesis about the Saturn's appearance? Because that's the only celestial body that's not a circle, that has like weird ears that never changes or arms next to them.
Well, I mean, we're gonna discuss it.
We're gonna discuss it after you
Alright.
just do some private brainstorming, use your best judgment. And then the second question is, obviously, the observations made with these celestial bodies cannot be made without Galileo's telescope. And we want to study if Galileo's telescope is good enough. How would you test it if you're a 17th century scientist?
We're just thinking.
Yeah, just think it out and maybe jot down some ideas, and we're open to discussion. Yeah.
Question, is Galileo's telescope like a type of telescope that people could make a Galileo, or is it like his personal telescope that he hasn't?
There's only one telescope in the whole.
There's only one telescope in the whole world.
He invented it.
Okay.
Yeah, but he would be able to share. How he made
Imagine
it
you
if
could
he-
grant, you were granted access to it.
Okay.
He would lend it to you.
Yeah, you would be able to test it if you can come up with an idea.
Wait, do you
We
guys
can't make
know
our
who made, did he make his own?
Yes.
Yeah.
See,
Okay,
yeah, I didn't know that.
because this existed, he didn't invent the telescope.
He didn't invent it, but he made his own. He,
Wasn't the initial, wasn't the innovation, the double lensing?
Okay, so he had the technology.
Yeah, so
But there were a couple people concurrently inventing some similar double lenses, but at the time, he was the only one privy to this particular telescope.
and he pointed to the sky.
Did the other ones not?
I say use it for, just for sailing purposes or.
Steve, yeah.
staring into the building and then they go across the way. You know, it's like just a
Doing
bit.
Yeah, okay, we're gonna take a vote before I open floor for discussion. So given all the deliberations that you have with Galileo's telescope, do you still decide to support him or refute his argument? We're gonna take a vote. Those who think that you're gonna continue supporting him, raise your hand.
Just, you gotta choose one or the other.
Yep.
I just-
Withhold your judgment, right?
Under,
That's
under pain of death. I mean, it's-
support or withhold your support letter.
It's very binary.
Maybe head to back with the church.
Yeah, so thoughts comments, questions? We have a bunch of other stuff to get to, but just, what do you think of this case study?
I mean, I'm an observationalist also, and I always find lots of problems with observational products, instruments, so I would have gone back, thought, oh, maybe something was wrong with Venus, we really didn't have those phases, and there's something wrong with the telescope.
You wish you could like send some current observationalists to like the Spanish Inquisition.
So I'm skeptical of observations,
Okay,
Yeah.
because the instruments are not
but
reliable.
yeah.
But would you come up with some ideas of testing it?
No, no, I mean, not, no, I don't know enough about telescopes,
Okay.
to be honest.
You could put a light from like something really far away and see if it's from like the tree to see if that's.
Oh.
Mm-hmm. But that's somehow, yeah, that's a good test, but it's somehow limited, right? Because it's 3
Refraction.
miles you're looking at and it's on Earth. And it's not like, hundreds, thousands of miles beyond the Earth, and you don't know what happens with the atmosphere beyond the Earth. So that's a good test, but it has limited. It appears, you have to make an inference between what's going on the Earth and the testing on the Earth to the actual extraterrestrial observations.
I mean, it might be asymmetrical. You could get a negative test if you had a single light 3 miles away and top of a mountain or whatever, looking at it, and it shows up as 3, and then you go and establish that it's only really 1. And you'd be like, the telescope doesn't even work in this case, so obviously it wouldn't be suitable in another case.
Well, no, I mean, you might say, oh, no, there's a special case there, because the boundary layer, there's turbulence, there's also, I mean, it'd be easy enough to come up with reasons why you wouldn't expect it to.
Uniquely look like.
Perfectly.
You see a double sun, like right at the horizon sometimes, right? It'll be, so, I mean,
So people are aware that there are optical effects.
Mhm.
I was thinking like a program manager, like I'd wanna, fund maybe an extra year, like, can you like figure this out, like come up with a theory to, hypothesis that would explain
There's
this,
already a theory.
continued observation.
Replication. is
Replication
the other
also.
thing. Like somebody else,
Filtering.
you make another telescope and see what you see.
Yeah, my mind went to like, can we have different groups, or like make telescopes, different styles, form an IPCC, like intergovernmental panel of celestial coordinates.
But I
and
keep funding
just, like-
Galileo, like you keep funding him. right?
Well,
You
him
keep working
too,
on the
but
problem.
also you want different
Yeah,
people who, maybe that guy's a crackpot and, that's, okay. I mean, my brain is like, anytime there's a new discovery now, and it's like, oh, this overturns conventional wisdom, it's almost always wrong, right? And so.
See, now, if this was more well known, right, you would have been able to use this to negate the Disney copyright on Mickey Mouse well before.
Yours are too low.
It's a prototype.
The general sentiment is a telescope MIP, pretty much.
Yeah, telescope map and,
How would you know that they're not prone to the same bias or error? Like, even if they all say there's an optical illusion, obviously we know today, but then all the telescopes that are made are subject to the same optical illusion. What happens to that? Do you confirm your hypothesis?
well, this
Well, you
is
can-
part of the myth, is to
Yeah.
examine.
Well,
how
you-
telescopes-
If that's the case or not,
confirm-
yeah.
You confirm the measurements as a function given potential similar biases in all the things, right? But if they don't confirm it, then you've got a negative result, and then you're better off, right? But if they do, then it's only subject to the caveat that all of these instruments may have the same bias.
Hmm.
Also have how many variations of a telescope can you make, is it, I don't know. So I'm supposing could they be wildly different or not? That's why you would want to compare it to no.
Right. Or you can observe something that's in between the distance between Venus and Saturn, and you could see whether it in fact shows phases or it has 2 years, and you would find no, it doesn't. It's full moons.
So more observations, variety of telescopes.
people in different parts of the world ideally would have
Replicating.
put different angles to the atmosphere. Because optical effects relate to a slant path.
Mhm.
That would be maybe, if they get the same result, that would be in my mind, more evidence for something,
Mhm.
or goodness of the telescope, I guess.
Yeah, that's a good idea. Do you want to take over
Yep.
from?
Put a telescope on a big mountain.
So like a telescope ensemble or something.
Yeah, so apparently the idea is that the simple historical case bears many similar characteristic of the scientific research that we do today, right? An observation refutes major hypothesis, but there is uncertainty within the observation that has to do with measurement equipment. And then you also want to validate the measurement equipment. And the actual history is much, much more complicated than this. I'll explain a little bit and then Ryan can take over about the philosophical message that we want to bring to the table. So in 1610, optics, the theory of optics was not well developed at all. Like people don't really know how refraction works very well. The Snell law was not, it was discovered, but it was not widely known. It was firstly really well formulated and discovered about 50 years after Galileo's observation. So actually Huygens, he also made some advancement in optics and was able to build larger and better telescopes also based on the theories about optics. And he was able to eliminate the ears of stat and then was able to see the actual rings. So that's how the case was resolved. And then Ryan will introduce us the philosophical messages that we would like to bring to the table.
I mean, even just listening to some of the comments, I feel like we could take this example and teach a bunch of different units from philosophy of science, but we had one in mind to begin with, so I'm gonna go ahead with that one. And that's the idea of holism, whether or not we can test hypotheses completely in isolation from other assumptions and hypotheses. So this quote and this photo here, this is Pierre Duhem. He worked about a little over 100 years ago. Experimental physics was a lot of what he was focusing on, so not astronomy at all. And he emphasized the idea that especially in like lab experiments, like in physics that he was focusing on, you can't test hypotheses completely in isolation. He says that physics is not a machine which lets itself be taken apart. We cannot try each piece in isolation and in order to adjust it, wait until its solidity has been carefully checked. Physical science is a system that must be taken as a whole. It is an organism in which one part cannot be made to function except when the parts that are most remote from it are called into play. Some more so than others, but all to some degree. And so you can reconstruct the line of thinking that we might have with the Galileo case and then draw an analogy with climate modeling, which itself can go in multiple directions. But so suppose we have this hypothesis, H sub G, which is just the hypothesis that the solar system is geocentric. And
So can I ask?
yes,
Under that theory, the main cycle of Venus is sort of locked with the sun's main cycle. So there's the epicycle and then there's the main cycle, because if the main cycle progresses around, then you would get full phases. Right?
In the rotation rate compared to the revolution.
Yeah, right. There's like a cycle and then there's an epicycle that is rotating around the thing.
yeah. So should there have been an expectation of full phases?
Yeah, I would think so, as
Well,
long
no,
as,
because
unless they're locked.
We're philosophers, we actually don't know. So we just take what historians said to be true.
So if you had, because the Earth is at the center, right? So it looks like, so Venus is going around and it kind of goes behind the sun and comes back, right? So they knew that. Right, but then they're assuming that the sun is also going around the Earth, right? So you have,
Well, in this picture,
This
because
better.
like the Ptolemaic system required epicycles, right? It
Right.
required cycles within cycles to get like the retrograde motion of like Mars and stuff
Right.
like that, right? And it's like a huge complex system. As far as I know, it predicted better than Copernicus's
Yeah.
model, like by a wide degree. So, but like the question is, is that, what would it predict, I guess? What did it?
somebody must have worked it out at the
Yeah.
time, so it wouldn't have been such an issue. Maybe
Right.
it was like phases at the time when Venus is between us and the sun.
Yeah.
Right, it's just so that would have been the difference. No, because they're here, they're looking at a whole year.
Yeah.
I don't know. We can look at that. That's homework.
Sorry, this is the minutia that probably are not important at all.
Well, it's interesting. So let's suppose though that we'll take Galileo at his word that we would expect. That Venus would only show a full set of phases under the heliocentric, but definitely not under the geocentric hypothesis. So then the telescope observations sort of seem to serve to like falsify the geocentric hypothesis. That's what we hopefully want to conclude. That's what Galileo wanted to conclude. And so HG, this hypothesis that Galileo thinks is falsified. But if we're thinking along the terms of holism, like Zuham talked about, we have to recognize that this hypothesis is not being tested by itself. Whenever you're doing a test or making an observation, you have equipment and background knowledge and things that are brought to bear at the same time as the hypothesis that you're interested in. And so it's actually a group of hypotheses that are being tested together. And so in this example, we have A1 plus A2 all the way through AN. You can probably fill these in a bunch of different ways. But like A1 would be maybe the telescope is a reliable instrument. A2 is Galileo is skillful at using the telescope because he's the one that made these observations and did the drawings. And we could even unpack these further, like A1 prime theory of optics that Galileo used or employed when he built the telescope is correct. And we could probably pull that apart even more. So the idea is that when you think a hypothesis is falsified, you actually have to, examine the surrounding pieces, things like the periphery, the observational equipment, and so on. And so similarly in climate modeling, I'll run through how I see the analogy, and then I'd love to hear some thoughts. So imagine the hypothesis that like clouds have an overall cooling effect on the Earth in a warming climate, or let's say in a climate where CO2 concentrations are slowly increasing. And that this was a hypothesis that was falsified by climate models. And so it's similarly still keeping the analogy, we think that this hypothesis is falsified by climate models because they show that clouds don't have this cooling effect, net cooling effect. But then again, we have to recognize that this hypothesis is being tested along with a bunch of other assumptions. And then the question is, well, what do we put in to fill in for A1, A2, all the way through AN? And then can we tease those apart? And so just a few ideas. I mean, we can think really broadly, A1, that climate models as a whole are reliable tools and that scientists analyze climate model results in a reliable way. But of course, we could also unpack climate models have different parameterizations and modules and interacting parts and some code that maybe isn't always employed for the most principled of reasons. And so there's a lot going on. And so we could also, just like we could look at the theory of optics to think more about the reliability of the telescope as an instrument, we could look at the different pieces of climate models to think about their reliability as a simulation tool. And so you probably can't see this very well, but it's just a depiction of some different submodels. Like the atmosphere module would have cloud parameterizations, aerosol representation, and so on inside of it. You have a sea ice submodel and land submodel and so on. And so the question of holism in this case might be like, well, can you tease apart how the different parts of the model are contributing to an answer that you think is good or an answer that maybe is wrong in some way? So thoughts, questions?
So I think there's a slightly easier analogy that you can use here, which is the physics of the climate model per se that you want to test, and then the drivers of the climate model, the inputs of the right. So, for instance, the increases in greenhouse gases or the changes in aerosols, which may themselves be incorrect, right? Because we don't know perfectly what aerosols have done, right? So my test is actually what happened in the real world, right? But I don't know what the actual inputs into the climate model were, and so I have a mismatch between the observed trend and the climate model trend. But it might not be because the climate model was wrong. It might be because the forcings were incorrect, right? And so there's a very clear distinction there of something that you could dig into, and so and that's a real example, right? So during the 2013, 2014 was like all the excitement over the pause or the hiatus, right? Which I think you read about at some point. And one of the things was, well, the models don't look like the real world, and the real world seems to be like kind of going down the bottom of the model spread. And it turns out that one of the reasons why this wasn't a big thing on the models was because the forcings were correct.
And so you change the forcing and then no, doesn't look like there's.
And well, so we discussed this as well, right? So if there's a model observation discrepancy, there's at least 3 different ways it can be wrong, and then there's that fourth thing. So you've got the drivers in the model are not right, the model is not right, the data is not right, or you're not comparing it properly, right? And all of those things have happened in history, right? And with the pause, it was all of this.
Yeah, so I guess that would be a more straightforward example rather than trying to look under the hood of different models.
But kind of to your point, to what Gavin was saying, that you can do this analysis at many different levels. Like you
Yeah.
could break this down and look at one process and then look at, okay, what cloud data do we have going into it? Or you could zoom out and you can look at our estimates of warming from our climate model into the 21st century.
Mhm.
Like this applies, I think, like within itself,
Yeah,
because
I
the
mean,
climate models are so complicated.
Yeah, I mean, the Duhem Quine, like kind of, many hypotheses being tested at once is a very general point. And it's one that we have often, I think, neglected in the field. There's often papers that come around afterwards and explain, oh, well, all these different things went wrong to make that thing wrong. But there's often a lot of papers that say, oh my God, the climate model was falsified, right? Which are extremely valuable.
One question I like thinking about is keep taking the more complex version of this, like if an earlier model and a later model, they have a very different like emergent behavior, or they have different equilibrium sensitivity or something. And then how possible or impossible is it to go back and point to particular changes that were made that contributed to that change? And how well can you explain by pointing to the different pieces of the model that, well, equilibrium climate sensitivity decreased by 1 degree because of changes X, Y, and Z, and we're very confident, and we're not confident in all of this.
I think in general, we don't have a good understanding of what all the pieces of our state of understanding are. If things are structural or if it's other parts of uncertainty, I mean, to some extent we do, in some cases we do. And in some cases, the whole point of a paper is to isolate down certain components so that you're just getting at one thing. But I think overall, we don't have the full clear picture of what our uncertainties are. And I think that's why we have a job partly.
Well, in a sense, the model is like, when you talk about ChatGPT and you're like, it's trained on, centuries worth of literature in all the world's libraries or whatever, and you ask it to write a Shakespeare, and it's like, well, what can you track it? How can you track why it wrote what it did? And you can't. And I don't think it's a bad thing, personally. It's part of what emergent behavior is. And, it's like, why does the model do a storm track that it goes around like that? And you're not gonna go to a certain spot in the code and be like, that's why. And so I don't.
But if something goes wrong, like if the model gets worse according to a bunch of metrics, it would be nice to be able to go back and say, these changes, these are the reasons why I went wrong.
I feel like
Well,
an analogy.
when you make graph, yeah.
I feel like an analogy might be like a house that was built over many centuries by craftspeople of varying degrees of skill. And the one thing you can say is that the house is standing, but the roof leaks. Why does it leak? Well, the roof is a little complicated. It was built by 5 different people. Why do the floorboards leak? Oh, I know or why do the floorboards creak? Well, I know who made those. And that guy was just bad at his job. And that's why they creak. So certain things are like that, and other things are just like a hodgepodge that you can't get your fingers into.
And usually these long-term responses in the model, like we discussed, climate sensitivity, for example, you obtain them after very long simulations, after you've done several changes in the model. It's hard to go back to one specific. That's the one that's the digit, for example. We could do it potentially if we had a model that we could run much faster. We could change single properties, fields, and see how the model responds.
But then we could build a demo model
Yeah,
that
we-
takes 3 months to
Yeah,
run.
but that's why we do now this kind of machine learning to see which one of these processes is probably
But
more.
we have a model that runs super fast. We could run the 8x10 model,
Yes.
right? But we never do.
But we could, if.
Well,
for
we could, but
example,
we
your
don't.
purpose was-
Nobody cares why the climate sensitivity of that model is different.
Yeah,
from
but
one
that
to the next.
particular model, no, I'm saying the version of the model that you're interested in to find out what.
But you're not interested in the version of the model per se, right? We don't actually care about the model. We care about what the model says about the real world, right? So we never go back if we think that we have a better model now. We almost never go back and then examine, why the old crappy model did what it does, right?
And this is a very GISS philosophy, though, that I think other modeling groups would object to.
To never look back.
Yeah.
Well, not to never look back, but to add and add and add and not strip something to its essence and try to be more on that understanding end of the spectrum rather than like, let's get the land use right, let's get the aerosols right, let's get the cloud right. This is a very GISS philosophy. Of course, this is a great model, but it is part of what I think a lot of people here have internalized is like, we need the matrix. And let's not just go to an aquaplanet and see why the jet stream does what it does under simplified conditions. Something it's just not a big part of the group.
Well, that's a little thing. So I think that those kinds of tests are total waste of time, right? But I'm only in charge, so you can decide what you want.
I'm just noting.
Time and money, we could possibly do this, all these kinds of different simulations, one by one at a time and see
But
what.
we're always resource limited,
So you think it's a waste of time because if you got a good answer, it still wouldn't help you.
because you wouldn't get a good answer. You just get an answer that they're different. You get an answer that, oh, this affects that, but what's the relevance to the real world? So what's
At
it
some point, NCAR and GFDL tried to understand why their model climate sensitivities were different. This is about 20 years ago. And they exchanged components. In the end, they couldn't really find anything robust. And there's something very nonlinear about what the climate sensitivity was. So I think they concluded in the end, like that was not a helpful exercise.
And this is not an esoteric question, right? So right now, the NCAR model, CDSM2, has a climate sensitivity of 5 and a bit, 5.3 or something. Okay, and now people have found errors in the code, right? So Zach, who's here, when he was working in Norway with Trudy, found a bit of code that seems to be a bit stray, that was like kind of messing around with the ice physics. The ice particle physics, and he wrote to Andy Gellerman, whose name came up earlier today, and he said, "This doesn't seem right. Like, where does this come from?" And they said, "Oh, yeah, no, that shouldn't have been there. We should have got rid of that." Now, there's one group in CAR that took that, fixed it, made one other change, and then claimed that this totally dealt with their climate sensitivity problem and allowed them to get a valid OGM simulation, which then they were not able to do. I had like a dozen conversations at AGU about this particular situation, and everybody at NCAR swears blind now that was not really important, and that if you just change that, it doesn't change the climate sensitivity at all. And apparently a paper is in the works. But then,
Is there a
well, a
paper?
paper, it's basically refuting the claims in the Zhu et al. Paper that I think people have accepted it was an error, but
But it doesn't
Andy
have an
Gellerman does not accept it was an error. It's just a feature. But so there's still huge uncertainty about why anybody's model's climate sensitivity changes, and despite enormous amounts of interest.
I thought CSM2 also had a bug or something where the Labrador Sea would kind of freeze on some runs, depending on just a small change in energy conditions.
I think that was something I saw in development. I don't know if that was something that was that's in the current version.
Oh. I just follow up. I don't know who mentioned it about using machine learning methods to diagnose changes in model behavior. Did I hear that?
I think that was Natasha.
I followed that on something like that. So sometimes you can't do single experiment, but if you build an emulator of your model, then you can perturb the parameters one at a time. The experiments now are much faster.
Yeah.
Oh, I mean, this is something that we are all thinking about doing here too. At least for parts of the model, maybe not for the entire model, but for part of the model.
Yeah, that would be an example, like along the lines of what you're saying. That's kind of making the model more simple to try to understand the quick changes. I mean, it's replicating all of the effects, but somewhat crudely in an emulator, right? To make it quick and thinking that the error is smaller than the differences in results, you know.
And so that would ideally be helpful for informing future model development or knowing.
Yeah,
So,
but also, it's also sort of poking around the house and figuring out what parts are creaky and
yeah.
loud.
Which parts are structurally unsound?
There you go, that's perfect, right? Ooh, we should keep this.
Okay, so I have a few other, I mean, so this is sort of the analogy and the big idea, the take home message is about this idea of holism. But philosophers of science have theorized about it in relation to climate models in a couple of different ways in the past, I don't know, like 15 years. And so I just wanted to share a little bit of that. Feel free to interrupt with questions.
And it's not our research, so if you're apart, that's fine.
Well, like, so these folks I particularly disagree with, but I'm gonna present what they have. So this is supposed to be a unique type of holism. That ostensibly arises from three features of general circulation models. One is this idea they call fuzzy modularity. It's getting at the fact that, climate models aren't like Lego blocks. You can't just take a piece out and look at it and know that if I know everything about it in this isolated context, I know exactly how it's going to behave when it's inside the model. Because the different parts interact, and they interact over time. You don't just get the results at the end and put them all together. It's a dynamic process. And so that makes it really hard to tease apart the different causal roles played by the different submodels. And these authors also talk about the idea of kludges, tweaks and tinkering and unprincipled changes made to code to get things to work together if two submodels aren't talking together in the right way. Just any changes that need to be made to get that to work. Kind of curious if this maps onto your experiences working on kind of models. Like, have you had to make these?
Tunings, we call them tunings.
Yeah.
Well, there's tuning,
Calibration.
there's tuning and calibration, and then is there any like, I don't know,
Sure.
fudged code that you have to?
Factors,
Yeah.
I've seen that in astronomy.
Okay, so for instance, we had a big problem calculating the albedo on a Greenland ice sheet because it would get too dark and then it would just melt and then just keep melting. And so we fixed it so that it was always 0.8, right? So we went back on complexity to something simpler because the complexity was not complex enough, right? So that might be valid. Yeah, we had.
We prescribe some relationships, for example, in the model, not,
No, but that's a parameterization. That's fine.
yeah. Well, based on observed, so the model doesn't calculate these relationships, you oblige the model to use them. More basic than parameterization. Parameterization adjusts to the model behavior.
There's a factor of 10 that somebody stuck into E3SM for the Bergeron ice process and then forgot to take out.
How was that discovered?
I'm sure it was a painful evening. I
I
think,
mean, I once deleted the call to the bottom friction in the ocean model, and we didn't notice for like 3 years. Oops.
But did it have a discernible?
Not a huge, no.
We prescribe certain parts of the model, like the seasonal cycle of something. That's also.
Well, it's not really a, I mean, like a kludge might be, so, you're not making enough deep water over the Denmark Strait, right? And so you put a pipe just over the Denmark Strait to kind of funnel deep water into the Denmark Strait. Now,
That's a kludge.
Yeah, I think that's a kludge because it's not a general
Yeah.
thing. It's like a very specific thing to deal with a specific problem. Now, there's some models that have done that, and then they took it out. They took it out in the LGM but they kept it but they didn't have it anywhere else, just for the Denmark strain.
I'd say there's like three layers to this. One is like first principles, so like conservation of mass and all that. And then the second would be like parameterizing things as much as you can based on observations or whatever. So like gas, air exchange or something, you'd be like, okay, it's proportional to the wind, but there's a constant and that is derived from field missions or something like that. And then there's like that of like, okay, here's this problem and we need to, like, too much water is going into the Arctic, so we need to just like route water somewhere else because it's like of that. Yeah, so that it's kind of like three levels of that.
So, finish your point.
And the last idea that they talk about is generative entrenchment. Sort of like the historical legacy of code, or the house analogy of, you know, you're not tearing down the whole house, it's starting from scratch. It's building on a foundation that's already there, and that might limit the types of changes or things that you can add. It's sort of like a path dependency. And so this is from a paper from Lenhard and Winsberg. They're two philosophers of science. And they think that for these reasons, I mean, I don't know if it's a direct quote, but they basically think it's impossible for scientists to be able to tease apart the reasons why a model is biased with respect to some observational data, or why it performs well compared to some observational data. They think it's not possible to go back and say it's because of these pieces here or something else. So they have a very skeptical sort of philosophical view on this, that I sort of disagree with, even granting that some of these things are fact.
So what's your opposition to this?
I'll show you. So, I mean, I've been thinking more about this idea of error diagnosis, attributing biases to particular parameterizations and this type of thing. That happens, not published that often, at least from what I've seen. Maybe it's published a lot more and I'm looking in the wrong places. But I think that this involves some sort of piecemeal understanding of the models, in a way that's not appreciated by Lenhard and Winsberg's analysis. I mean, just one more point about they have those three pieces, those three reasons for being skeptical, and then they look at AMIP, the first AMIP as their evidence, so the first atmospheric model in a comparison project. So they go from the skeptical claims about individual models, and then they look at a huge model in a comparison project and say that is sort of evidence that they're right. And I think there's a huge difference between figuring out why models are giving you different answers from one another versus figuring out why a single model is giving you answers that are good or bad.
It doesn't have to be one or the other though, right?
No,
I mean, for some
no.
variables, like the Amazon rain has always been hard to figure out why the heck we're always underestimating. Other things, it's sort of like, I know exactly what it is and I'll fix that, you know? So, I mean, it's just not binary exactly.
No, it's a spectrum though.
Yeah.
I mean, it's very
Right.
rare that you see something and you say, oh, yeah, no, and that was that one line of code, right? You know, because mostly you're looking at emergent property, which is a function of 50 different things,
Right.
as opposed to, you know, some process-based diagnostic
Yeah.
where we have had success and say, oh, well, you know, in this circumstance, in this case, then we're not moving by enough, or we're not,
Yes.
not training it.
Right.
But it's a function of the observation, right? So the extent to which an observation is an observation of the emergent properties, right? Then it becomes much harder, right? So the extent that an observation is actually close to a process that you might have coded, right? And you're just looking at that process, then you're much closer to being able to just say, oh, you know, I can fix it.
So, and with the single model versus multi-model, like in a single model, you have structural uncertainty. In multi-model context, you have structural uncertainty and every single coding difference between the models. So I think that there's an added layer of difficulty to tease apart why.
That's the
Well, yeah, I mean,
structural
yeah.
uncertainty, right? The difference between the models.
Yeah, but
Well, you got,
well,
sometimes, so within one model, you have parametric uncertainty,
yeah, okay,
right? And then across models, you have structural uncertainty.
okay, so that's.
But you're right. I mean, if you have an error in the multi-model mean, and like you have, I mean, that's an emergent property of emergent properties. That's like it's almost impossible to tell why that is.
Yeah. So I don't know how we're doing on time, but we have a little bit more.
Wonderful. We're okay. We can go a little bit over as well.
Okay, so another thing. I mean, I guess maybe just some evidence to back up this idea that error diagnosis is a regular feature of climate modeling, at least in some sense. Like the history of climate modeling involves a lot of, we know that these parameterizations are bad in these ways, and we are going to work to improve them, and hopefully the overall model performance will.
That's not a great example though, 'cause that's just an uncertainty, but it's now actually, you don't know where any of them are wrong. One assumes that most of them are wrong, but we don't actually know what the right answer is.
I suppose, but I don't know, the IPCC 6 says with some degree of confidence that I don't remember, that the cloud radiative forcing is, pretty much definitely, net positive rather than possibly net.
This is the feedback,
Yeah,
right?
Yeah, this can't be, cloud radiative forcing is like -20 watt, like climate logical, this is.
Yeah, this is the cloud radiated feedback.
yeah, that's, I don't know, well, let me just,
So
well, our friend and collaborator Travis O'Brien put this together, but I wanted to just make sure I got what he actually did, because he made the figure himself. He said estimates of simulated cloud radiative forcing were acquired by manual digitization of blah, 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 multiplying equilibrium, climate sensitivity, and cloud feedback columns in tables, blah, 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 of Zelenka et al.
Oh, so it's the feedback times by the climate sensitivity, so it's the degree, so that's not in what's mixed. So the feedback is in K, no, what's per K, multiplied by the climate sensitivity is what's per square meter. Right,
I don't know.
but what is that value, what is that quantity?
I don't know why that's useful.
You mean what like the label on the axis should be?
The unit.
Yeah, I mean,
No,
what,
the unit, I believe.
okay,
is
the
still-
unit is right, but
Yeah.
what is the quantity that you're now calculating?
Is this a watt
Like
per
where
meter
do you
square?
change or?
Yeah.
like, I don't
Just
know.
the watt, isn't it? So watt.
It's the contribution of the cloud feedback to
The
climate
watt per meter square
sensitivity.
per K, which makes K the numerator multiplied by sensitivity, which is, or has K the numerator multiplied by sensitivity.
So
K
this
cancel, don't they?
is
Yeah.
the change in, this is the change in,
Change in cloud radiative forcing with 1 degree K increase in temperature.
Yeah, multiplied.
no, because it's not with 1 degree.
So per
This
K.
isn't per Kelvin, this is total.
I thought it was,
they were.
For
the
2
first
times CO2,
Kelvin.
if you multiply by the climate sensitivity, this is for 2 times CO2.
So it's the absolute cloud, it's the absolute watts per square meter per Kelvin, but they're multiplying it by the total. So it's the total radiative change caused by clouds, but that's. Now-
Caused by cloud feedback under a 2 times CO2
Right, yeah,
scenario.
yes,
So we need to.
but it's not cloud radiative forcing.
no.
Yeah, it's a weird thing.
I mean, I think the units are right, but it's not cloud
Yes.
radiative forcing.
It's not cloud radiative.
Is it a meaningful result still?
Well, I mean, your point is that clouds feedbacks had a big increase in spread in AR6, right? That's important.
Well, the point here is that it's, not positive, well. There's an upward trend from third assessment report to, AR6.
Oh, we're not using the models as if they were a probability distribution function. What would be the epistemological basis for that?
So is your point going back to
You'd
the
be the first
holism
person to do
argument
it.
that this is a hypothesis that was recently that the feedback was cooling, that was a hypothesis recently disproved, and this is showing that?
Yeah,
Is that what's getting?
and
back
that
here?
it was refuted, well, that this happened as a result of specific changes that were made to the model that, like the boundary layer parameterizations, being updated and.
Mostly cloud microphysics.
It sounds still in line with what you've been saying. I don't know what the prior assumption was, as long as you're not comparing the prior assumption of radiative forcing to what this is. Cause that's always been a correct conclusion on our part, right? That cloud radiative forcing is negative.
Yeah, 'cause that's that's the total change in the TOE balance if you took away all the climate.
Yeah, so you just
Right.
gotta make sure that the prior hypothesis that this disproves, you're comparing like to like, I would guess.
Okay. We're gonna have to talk to Travis as well.
Yeah.
But anyway, hopefully it's not controversial to say that some model performance improves and some of those improvements can be attributed to updates to parameterizations. even.
Sure.
So we were thinking that a similar type of thinking, if you think of parameterizations as components in the overall model, a similar type of thinking might apply to the world of AI models and explain more artificial intelligence. Which, and Dan wanted to say something about this.
So now I don't feel confident about the.
But this is like, so, I mean, we're at a boundary here, right? You know, and there's a lot of fertile back and forth when you look at those boundaries.
Yeah.
So it is often sometimes a little uncomfortable.
That's true. Okay, so Ryan and I and our collaborator Travis O'Brien just submitted a perspective piece to geoscientific modeling.
Geoscientific model development.
Development. Yes, GMDIA perspective piece, because climate scientists started using machine learning, and then obviously everybody knows that black box is not something we want. And then there's this new emerging research area called explainable artificial intelligence, or XAI research, trying to shed light on what black box models, what machine learning models are doing. And we wrote a perspective piece calling cautions for this kind of approach about what XAI can really do. We need to have a realistic expectations and we make our argument by drawing the comparison between machine learning models and dynamic climate models. So what XAI methods are doing is perturbing the input and output and trying to find out which inputs, which subsets of input are responsible for the black model making this prediction. So you can also think of them as attribution methods. You can do the same with dynamic models. Just perturb the input and output and see twiddle some switches and see what changes are made. And we term this statistical understanding. Is really not giving you how exactly the model works within itself, but the input and output mapping, we can get that. So it's a statistical model on top of the input and output data. But if we look at next please, if we look at the dynamic model development, and a lot of you know much better than us, is that sometimes you can pinpoint the specific modeling component and call that this is the reason, this parameterization is the reason why this model blew up, or this parameterization is the reason why this works. If we substitute, for example, this parameterization with real world data, the model performance improves. So we think that machine learning practitioners can do the same with the black box model if they pay attention to the model architecture. So think of this black box as a puzzle pieces, but when you build the puzzle pieces, you build components into them so that later you can trace what's going on with the model and which parts of the model are doing exactly what. Next piece. And then we offer 3 case studies done by actual scientists in physical. This is in physical sciences, and this is one that's not. I'm not going into detail, but the idea is that when they build a model, they consider layers of neurons or put Fourier transformations so that when you diagnose them, you know that this specific model components are responsible for the model to get this kind of research. This can also be done post hoc. There's a new method called GAN dissection, generative adversarial network dissection, which is when after you train a neural net and you iteratively train adversarial neural net to understand like which subsets of neurons are in charge of like these pixels. And when you can really tell by if you turn off these neurons, these pixels, the corresponding pixels just disappear. So this is the general gist that we think that component level. If we focus on the component level understanding the same way that dynamic modelers are doing, then we can improve machine learning models in the same way. And there's a lot to be learned from how dynamic modelers are developing their models. And the last thing that I want to point out, and Ryan can tell you more about it, is that we're actually writing a grant proposal with a sociologist of science in NCAR, trying to understand scientists at different modeling centers, how they diagnose errors. Well, number one, what is an error that's worth fixing? Right, some errors, as you mentioned, are not really worth fixing, and some are. What is an error? What do scientists think are, how many scientists think that are errors are worth fixing? And what are the practices that how do they do that? How are the error diagnostic practice documented and communicated within the community? And then the last question is, how can we do better in terms of fixing errors? So we would really love, if we get a grant or after you get the grant, be able to work with the GISS scientists as participants. And you had a question?
Yeah, so are you thinking about, so a neuron, right? So are you thinking of that as representing one process, one physical process? Because obviously like a neuron takes into account, has inputs from all the previous layer and all the other neurons, right? And those themselves are some combination of processes that have varying roles on that particular, what goes into that neuron. So you can understand like the role of one neuron, I guess, but I guess that's not understanding in the sense of thinking like the role of a particular process.
Yes.
Okay.
So in the Ganda set case, it was in computer vision, and they don't really identify processes so much as like the causally relevant neurons, to the point where you could even just turn them off, and then all of a sudden the image has bigger doors now, or whatever it is, and they were able to do it with a decent level of precision, where they even had like a paint application that was just based on the Ganda set method that they had. But a case where you would have like process knowledge would be the one on the left, which is an example from like the physics informed machine learning, where you have like a particular layer or set of layers in a neuron that's like responsible for different energy conservation, something like that. And so that, well, this whole layer is doing this activity, but it's ensuring that.
Yeah, I would say by and large, that most of those layers do all of the activities themselves, like in different proportions. But each layer does everything. Maybe there's a final layer that does like the mixture thing is conserving energy and so forth. But I'd say overall, they're doing all of the components simultaneously.
Yeah, so that's a call. When we build machine learning models, we need to think that this group of neuron is responsible for this process, and that group of neuron responsible for that process. So when we diagnose them, we can isolate which group of neuron are doing what, instead of building a whole black box. If they're trained the current way that it is exactly what you said. Everything is doing all the things.
You're trying to, so what you're philosophically arguing is training particular neurons to represent only one process in a model. Is that only one component parameterization?
Or is the hope that the neurons sort of self-organize in some way and they sort of naturally subset themselves to certain processes?
It's more like when we build a model architecture, we should have to have the component.
Okay, so here are some real examples that I've seen, like, AGU last. There was one talk where they had a process-based parameterization that had like 4, 5, 6 variables. And it works okay, but they wanted to make it faster. And then they did a machine learned version of that same parameter, and then they found that really they could knock it down to there's only 3 degrees of freedom, not 8. Right, and so the neural net that they had didn't fall neatly into this set of variables is working on that process, this is working on that, but instead it was finding a larger pattern that actually found kind of correlations presumably between different parts of it that the process modelers had brought out independently. But I guess this was Kara's paper, wasn't it? Yeah, that's that. So Kara's paper shows, and maybe I'm getting it wrong in terms of the number of different variables. Maybe it was 4 and it went down to 3.
It's 3. It ended up being 3 when like the standard is 4, right. But it did better at 3 than the 4 did.
Right, exactly. So you have an improvement in parameterization that was discovered using machine learning, right? But that wasn't. But
because it exhibits less sensitivity to those other parameters.
Right.
But I worry about that when you put that whole thing into a full model, because maybe those things have little, they affect slow trending of feedbacks and things. So I feel like that can be done, but I feel like it's still a little bit worrisome sometimes in a full model.
Did they put it into a full model?
No, there's no way to advect those quantities around.
So then it's to your training data set, though, I guess that's a question, then, Greg's raising, what training data do you use, or how do, what output do you?
Yeah, like in different,
It's an arbitrary, more complex model. What?
It was just one time stuff.
but I see your point, yeah, I mean,
This is something also we're interested in about if. Like, the practice of diagnosing errors is done. How is that gonna be changed or made more difficult or better or worse or whatever when machine learning as it continues to be increasingly used?
So, but that study, yeah, pokes down into like, is there some efficient way of representing this, whether or not I can actually use it? Is it somewhere there in the mix? Like, what is the complexity of my problem if I just isolate this in this very simple way? Without necessarily how do I then put it in, but just maybe some understanding of that one process, I guess. I don't know if that answers anything, but it is, there are little guardrails around it.
Yeah, like, you have to hope that it doesn't interact in a funky way.
Oh, and then there was another example where, so take, did you read about neural GCM? Was a paper on Archive, maybe like a couple of weeks ago. And what they've done is they built a dynamical core that fits on a GPU chip in JAX, I think. So that's very much like what we're doing in the old school dynamical cores. And then they learnt the entirety of the column physics from the ERA5 reanalysis. So all the source terms, boundary layer mixing, radiative transfer, evaporation clouds, all of it in one column. And they showed that it actually works quite well, right? But there's no distinguishing of the key processes, and so you can't use it as a climate model, right? So it's fit for some purposes, making weather forecasts, but it's not fit for other purposes. And so by kind of like squeezing everything into the black box, you lose the ability to ask certain questions, like what would happen if just this thing were to change. And and because they've learned it from ERA5, there's no way of telling what you should do if carbon dioxide doubles. There's no carbon dioxide term, right?
Presumably it's way faster than.
Super fast.
So we're at about 2:07. I don't think there's something in this room right after. So if people want to stay and continue chatting, you're welcome to. So if you guys have more to talk about, but I do want, just so people know, just be cognizant of the time if you have to go somewhere else.
I'm happy to stick around and chat. Anyone wants to.
I'm so glad that you guys like the topic of machine learning, because that's what I'm gonna do next February.
You just got a month for that.
Kara Lamb would be very good probably to chat with.
Yes, yeah, so she was the one.
Yeah,
Okay,
she's at Lead
She's engineering,
Engineering, okay.
but yeah, she gets some of her funding through Lead, she's associated.
Yeah,
Yeah.
so she's at Columbia. She's also been to GISS a few times. She goes to a lot of cloud meetings.
Yeah.
So I'll give you her. She's like.
So I sent you a link about the.
I saw that, yeah.
We didn't
So-
like because it kind of ended.
Oh.
Like, thank you guys. This was really awesome.
Thank you for hosting.
Yeah, thank you for, and
So,
for the people still in the room, we'll be doing this in February again.
so the picture there is right. So the geocentric thing thought that
I
Venus only rotated in between the Earth and the Sun.
Oh,
It did not go around. And so when it
kind of
disappeared,
locked
it was
into
because it
cycle.
was in
We're
front of the
probably
Sun.
gonna end
You
the
can't see it
online
because of the
meeting
sun,
here.
right?
Oh,
So
okay.
it, so they
people
thought it was
that are
like that in
online.
this case.
So-
Yeah.
Okay, that makes sense. I remember there used to be a website that had like a model of the Ptolemaic model, and you could like zoom in on all the epicycles. It's insanely complicated.
Of course, it's just like a Fourier series. Like if you go,
Yeah,
if you go down with enough Fourier series, you can find, you can get almost infinite
yeah.
precision, right?
Yeah,
You got it?
yeah.
Yeah, let's look at the.
But that's a classic example. Where they're not
Guys, I-
informative of the actual process.
Right,
Because you can't